Hey, Math 30-2s. Today we're going to look at some exponential functions. We're going to analyze them. Step one, let's define an exponential function. So an exponential function is in the form f at x equals a times b to the x. A can never equal 0. 0 times anything will give us 0. B must be greater than 0. Our base must be greater than 0. And it can never equal 1 because 1 to the exponent of anything will just keep giving us 1. So the graph of the function has the equation y equals ab to the x with the same restrictions. Comparing the graphs of y equals 2 to the x and y equals base of 1/2 to the exponent x. So let's do y equals 2 to the exponent x. The values of a for 2 to the exponent x, a is 1 and b is 2. For y equals 1/2 to the exponent x, a is still 1, b is now 1/2. All right. Complete the table of values below and sketch the graph of the exponential function with the equation y equals 2 to the x. So let's do that quickly. When x is -3, if I plug that in, y would equal 2 to the -3, which means 1 over 2 cubed. So y is 1/8. When x is -2, that'll be 1 over 2 squared, or 1/4. When x is -1, that'll be 1 over 2 to the first, or 1/2. N of the exponent 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. Plot those points on the grid and graph and join the points. So when x is -3, y is 1/8. That's about right there. -2 and 1/4. -1 and 1/2. 0 and 1. 1 and 2. 2 and 4. 3 and 8. 4 and 16 is like way up there. All right, so we connect these. This graph should never touch the x-axis, and it expands up like that. So that's the graph of y equals 2 to the x. Beautiful. Complete the table of values for the graph of y equals 1/2 to the x, where x is any real number, and sketch it on the grid. So let's do the same thing for y equals 1/2 to the exponent x. So when x is -3, we get y equals 1/2 to the exponent -3. That negative exponent becomes positive if I take the reciprocal of my base, make the exponent positive. So it really just becomes 2 cubed, which is 8. So when x is -2, 1/2 to the -2 becomes 2 squared. 1/2 to the -1 becomes 2 to the first. 1/2 to the 0 is 1. 1/2 to the first is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8, and 1/2 to the exponent 4 is 1/16. Perfect. Let's plot those points on the grid and connect them. So now when x is -3, y is 8. And when x is -2, y is 4. And -1, it's 2. And 0, it's 1. And when x is 1, it's 1/2, and then 1/4, and then 1/8, and 1/16. So now this graph goes like that. It still crosses right there, and it should never touch the x-axis again. So if I label that one, this green one's the graph of y equals 1/2 to the exponent x. All right. Part D. An asymptote is a line whose distance from a given curve gets closer and closer to 0. The above graph's the x-axis is called a horizontal asymptote. The x-axis is a horizontal asymptote as both these graphs approach the x-axis. There's our x-axis, but they should never touch it. So my graphs touch the x-axis because my pen isn't fine enough, but we should say that the graphs are always above and they're approaching that x-axis, that asymptote, but they're never going to touch it. So let's complete the chart. For y equals 2 to the exponent x, look at that graph if you have to, and let's write down all these things. The domain. The domain is x. X goes forever to the right and forever to the left. So x is any real number. The range. Well, we said that there's an asymptote on the x-axis, so all the values for y are greater than 0. They're above the x-axis. They never touch the x-axis, they must be greater than 0. If the graphs never touch the x-axis, then there is no x-intercept. Right? They approach it but never touch it. The y-intercept, it crosses the y-axis at 1. The equation for the asymptote, the equation for the x-axis is y equals 0. Let's do the same thing for the graph of y equals a half to the exponent x. Again, the domain, this graph for x goes forever right and forever left, so it's any real number. Y is still above the x-axis, so y is greater than 0. This graph still never touches the x-axis or crosses it, so there's no x-intercept. Crosses the y-axis at 1, and the asymptote is the x-axis, which is the equation y equals 0. Part E, complete the following statements using the words increasing or decreasing. So f at x equals 2 to the x, example of an increasing function. Right? As x gets larger, y increases, whereas f at x is a half to the exponent of x is an example of a decreasing function. As x gets larger, y decreases. All right. Next page. Notice that the graphs of 2 to the exponent x and 1/2 to the exponent x are reflections of each other in the y-axis. That's a neat thing to notice. Exploring the values of b in y equals a times b to the x, where a is 1. So use a graphing calculator or other technology to sketch the exponential functions with these equations. So get out your graphing calculators and let's type these equations in to our y equals screen. All right. So my y equals screen, I'll clear everything. And y1 is going to equal 3 to the exponent x. 3 to the exponent x. And y2 is going to equal 10 to the exponent x. And y3 is going to equal 1/3 to the exponent x. And y4 should be 1/10 to the exponent x. Very good. And now we want to graph it on the grid that's similar to the one in our notes. So go to your window setting, and we can make x go from -10 to 10. Maybe let's just go from -5 to 5. That should be lots by a scale of 1. And let's make our y's go from maybe -2 to 20. Scale of 2. Great. So now if I hit graph feature, here's the graph of y equals 3 to the x. Here's the graph of y equals 10 to the x. Here's 1/3 to the exponent x. And here is 1/10 to the exponent x. So let's graph these on our page here. All right. So y equals 3 to the exponent x. Looks something like this. It's still got a y-intercept of 1. That's the graph of y equals 3 to the x. Color coding the blue one. Y equals 10 to the exponent x would look like this. Again, it shouldn't touch that x-axis. Y equals 1/3 to the exponent x should be a reflection of the blue graph in the y-axis. And finally, y equals 1/10 the exponent x should be a reflection of the green graph in the y-axis. All right, so there are 4 graphs. The value of b affects the steepness of the graph as x increases. Complete the following statements using the words increasing or decreasing. So, when b is greater than 1, the curve increases more sharply as b increases. Right? So when b is greater than 1, in these two situations, 3 and 10, as b increases from 3 to 10, the green curve increased more than the blue curve, so it's increasing. When b is between 0 and 1, so 1/3 and 1/10, what happens to the red and black curves? Well, as b increases 1/10 to 1/3, the curve decreases more sharply. Sorry, as b decreases, the curve decreases more sharply, right? So when it goes from 1/3 to 1/10, when it goes from red to black, it's decreasing more sharply. Without using a graphing calculator, make a sketch on the above grid of the graphs of y equals 5 to the x and y equals 0.2 to the x. So 5 to the exponent x, and if I want to graph that one, well, if the blue one is 3 to the x and the green one is 10 to the x, 5 to the exponent x should be right between those. All right. And if I want to graph 0.2 to the exponent x, well, 0.2, we know if I want to write that as a fraction, that's the same as saying y equals 2/10 or 1/5 to the exponent x. So where is that one going to appear? That one should appear right between the black and the red graphs. All right. So if you graph them on your graphing calculator, you'll notice that those are correct. Right? Verify them on a graphing calculator. State the x-intercept for each of the graphs of the form y equals b to the exponent x. So if I look at all these graphs, none of them should cross the x-axis. None of them cross the x-axis, so they have no x-intercept. F, state the y-intercept for all the graphs. Well, all these graphs should have crossed the y-axis at 1. You can check on your graphing calculator. We did it correctly up there. So they all have a y-intercept of 1. State the domain for each of the graphs. Well, again, every one of these graphs goes forever right and forever left. So our domain is any real number. And every one of these graphs is above the x-axis. So y should be greater than 0. State the equation of the horizontal asymptote. Well, the horizontal asymptote is the x-axis, which has the equation y equals 0. All right. Let's look at the special function y equals e to the exponent x. In math, the number represented by e is an irrational number like pi, which occurs naturally in finance, the natural sciences, and computer science. The value of e cannot be expressed as a fraction, but it is equivalent to the following: 1 plus 1 over 1 plus 1 over 1 times 2, and so on. Or we've looked at factorial notation. It can be written as factorial notation thusly. More and more accurate approximations of the value of e can be found by adding together more and more terms of the pattern above. So complete the following table to approximate the value of e to the nearest thousandth. All right. So number of terms. First term is 1. When there's 2 terms, it's 1 plus 1. 1 plus 1 is 2. 3 terms, 1 plus 1 plus a half, 2.5. 4 terms, 1 plus 1 plus a half plus 1/6, 2.667. So keep going with your calculators and figuring that out. This is going to be 1 over, keep adding that up, and you should be able to fill in that chart. So pause it and do that, and then you can check and see if you got it right. So this is what our chart should have looked like if we followed that pattern correctly. So an approximation for e to the nearest thousandth, we know after 7 and 8 terms to the nearest thousand, it stays as 2.718. All right, so a more accurate approximation can be determined by using the e key on the calculator. So the e key on our calculator, if you want to press that, our e is above the division sign, so you go second function e, and we find that to 9 decimal places. So let's write that out into our notes. So that should be 2 decimal 71828 1828. So that's what the calculator displayed. Sketch the graph of the exponential function with the equation y equals e to the x on the grid below and determine the following characteristics of the graph. So it just means it's got a base of e, which is 2.718. So we can graph that on our calculators. Let's go back to our y equals screen and let's just clear all these. And e to the exponent x, second function e to the exponent x, and y equals second function e to the exponent x. And we graph it. And it looks a lot like the other exponential functions. All right. So let's graph that in our notes. It's still going to look like this. It's going to cross the y-axis at 1, and it's rising up like that. Right. So this key point here is 1. The domain of this function is still any real number. It's still going forever right and forever left. The range is still above the x-axis, so y is greater than 0. There is still no x-intercept. The y-intercept still is 1. And the asymptote is still the x-axis, which has the equation y equals 0. All right. So it's just a special exponential function that has an irrational number as a base. All right. Let's study the value of a in y equals a times b to the x, where a is greater than 0. So consider the following functions with the equation in this form. Graph the functions using a graphing calculator and sketch the graphs on a grid. All right. So let's do that with our graphing calculator. All right, so we type these equations in. y1 is 3 to the x, y2 is 2 times 3 to the x, y3 was 5 times 3 to the x, and y4 is 0.5 times 3 to the x. Change our window setting, maybe so we have an x max of 10, all right, instead of, a y max of 10 instead of 20. And then let's hit graph. So there's 3 to the exponent x. Yeah, we've seen that one before. 2 times 3 to the x. Yeah, looks like it's just moved up a bit. 5 times 3 to the x. Well, that one gets moved up quite a bit. And a half times 3 to the x. Looks like it got moved down a little bit. All right, so let's sketch these in our notes. Okay, so 3 to the x. Well, we've seen that graph already. All right, that's the graph of y equals 3 to the x. And 2 times 3 to the x. Well, it's the exact same shape, but it just got moved up a little bit. It actually should cross that axis at 2 right there. All right. And y equals 5 times 3 to the x looked like this. And y equals a half to the exponent x. That should look like that. So all the same shape, just where they showed up on the graph. All right, so you've got that in your graph, you've got that in your graphing calculator. Complete the following table for these equations. Value of a in y equals 3 to the x is 1. The value of b, base is 3. The y-intercept of the blue graph is 1. Look at y equals 2 times 3 to the x, our green graph. The value of a is now 2. The value of b is still 3. And the y-intercept is now at 2. Look at y equals 5 times 3 to the x. The a value is now 5. The b value stays as 3. The y-intercept, if you count that off, is now at 5. and y equals a half to the exponent, or 1/2 times 3 to the x. The a value now is 1/2. The b value is 3, and it should cross the y-axis at 1/2. So consider the graphs of the equations. What is the relationship between the a and the y, the value of a and the y-intercept of the graph? Well, a equals the y-intercept of the graph. All right. Example 1. Without the aid of a graphing calculator, explain why none of the graphs below could represent the exponential function f at x equals 5 times 4 to the exponent x. Well, this function should have a y-intercept of 5. We're told this function has a y-intercept of 4, so that's no good. Our original function have a y-intercept of 5. Part 2 does have a y-intercept of 5, but our graph is an increasing function because b is 4. So b equals 4 means increasing function. And this graph is a graph of a decreasing function, so no good. And part 3, our function f at x equals 5 times 4 to the x has an asymptote of y equals 0, meaning it never crosses the x-axis. So that can't happen. So this graph is no good. All right. Exploring the value of a in y equals a times b to the x, where a is less than 0. All right, so we recreated the graphs from the previous page right here, 3 to the x, 2 times 3 to the x, 5 times 3 to the x, and a half times 3 to the x. Use a graphing calculator to sketch the graphs of the following on the same grid. So if you just want to change those all to negative signs in front, and let's see what we get in our graphing calculator. All right, so go to your y equals screen and insert a negative sign to each one of these equations. So make all these graphs the negative. And now if I hit graph, let's see what we get. Well, it doesn't look real great because we have a y minimum of -2. So that's not nice. Let's go change our y minimum to -10 in our window. And then we'll see a better picture here. So go to your window and make our y minimum -10. Now hit graph and we'll see the same kind of picture we should draw in our notes. So there's negative times 3 to the x. There's -2 times 3 to the exponent x. Here's -5 times 3 to the exponent x. And here is -1/2 times 3 to the exponent x. So let's graph those in our notes. Y equals negative of 3 to the exponent x. So our graph for 3 to the x is right here. We're going to do the opposite of that. Where is the, there we go. So there's 3 to the exponent x. And -2 times 3 to the exponent x. It's right there. And -5 times 3 to the exponent x. It's right there. And finally -1/2 times 3 to the exponent x. Should be right there. Right? Oh, don't forget all these have arrows going that way that never touch the x-axis. So how do the graphs of 5 through 8 compare to the graphs of 1 through 4? Well, quite simply, they're reflections in the x-axis. Right, every one of those graphs just got reflected in the x-axis. So complete the following table for functions with equations in the form y equals a times b to the x. Y equals -3 to the x. The value of a now is -1, and the y-intercept is -1. And if I look at the graph, the y-intercept is -1. For y equals -2 times 3 to the x, the value of a is -2, and the y-intercept is -2. Y equals -5 to 3x has an a value of -5 and a y-intercept of -5. And y equals -1/2 times 3 to the x has an a value of -1/2 and a y-intercept of -1/2. All right. So complete the table comparing the characteristics of y equals a times b to the x when a is greater than 0 with y equals a times b to the x when a is less than 0. Well, when a is greater than 0, so y equals a times b to the x where a is greater than 0, those are all the graphs at the top of the page that were already drawn in there. So the domain, x goes forever right and left, so any real number. The range, y is greater than 0. All those graphs are above the x-axis, never touch it. There is no x-intercept because the graph never touches the x-axis. The y-intercept is 1. No, it isn't. The y-intercept is a. The y-intercept is a every time it moves, every time the value of a changes, but the asymptote is still the x-axis, which is y equals 0. If I look at the graphs that were below, when a was negative, less than 0, the domain x still goes forever right and forever left, so it's any real number. Now the range is less than 0, so all those graphs are below the x-axis. All the y values are negative. It still never touches or crosses the x-axis. There's still no x-intercept. The y-intercept is still the a value, but now the a value is less than 0, negative. And the asymptote is still the x-axis, which has the equation y equals 0. So are there any differences in the above table? If the base of the exponential function is between 0 and 1, you can investigate in your graphing calculator, check it out, then you come back here and find out the answer. So pause it, check it out. Once you've checked it out, you should find out that there are no changes to the graph of the table above if the base is between 0 and 1. F, the shapes of the graphs of exponential functions with equations y equals a times b to the x depend upon the value of a and the value of b. Investigate using your graphing calculator and complete the following table. So let's draw some graphs on our graphing calculator when a is greater than 0 and b is greater than 1. So let's go to my graphing calculator and let's clear all these. That first box has us finding out if the graph increases or decreases and where it does that. If a is greater than 0 and b is greater than 1, so let's say we have a graph like a is 2 and b might be 3 to the exponent x. So with a 2 that's greater than 0 and b 3 that's greater than 1, if I graph it, that's the graph of 2 times 3 to the exponent x. All right. Remember how to label our quadrants? Quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So, like it says in our notes, this graph increases from quadrant 2 to quadrant 1. It starts small in quadrant 2, and as I get to quadrant 1, that graph, those y values are increasing. All right? Great. Let's see what happens with the graph of y equals, let's do a is greater than 0 and b is between 0 and 1. So keep the a value of 2 and let's make our b value, instead of 3, let's make it 1 divided by 3. To the exponent x. Now let's graph that one. So now our b value is between 0 and 1. So here's what that graph looks like. So this graph looks like it's going, y is very large in quadrant 2, and it's getting smaller as I move into quadrant 1. So how would I write that in my notes? Well, I would say that this graph will decrease as it goes from quadrant 2 to quadrant 1. So that's how I want to write in here. The graph decreases from quadrant 2 to quadrant 1. All right. You try what happens to the graph when a is less than 0 and when b is greater than 1 or b is between 0 and 1, and fill in these boxes accordingly. So pause this, try it on your graphing calculator, and complete these boxes. Then you can restart it to get the answers. Alright, so here's what you should have. When a is less than 0 and b is greater than 1, the graph decreases from quadrant 3 to quadrant 4. And when a is greater than 0 and b is between 0 and 1, the graph should increase from quadrant 3 to quadrant 4. Alright, if you did them correctly on your graphing calculator, you would see that. So finally, the characteristics of the exponential function, f at x equals a times b to the exponent x. Use information from the previous explorations to complete the following. The y-intercept is a. Whatever the a value is, that's going to be our y-intercept. There is no x-intercept. It never crosses the x-axis. The x-axis is called a horizontal asymptote. The domain is x is any real number. These graphs all go forever right and forever left. The range depends on the value of a. If a is positive, greater than 0, the range will be y is greater than 0. And we haven't been stating it correctly. If I want to do a complete range, we should say y such that y is greater than or equal to 0 and y is any real number greater than or equal to 0. If a is less than 0, then the range will be below the x-axis, so y such that y is less than 0 and y is any real number. That would be the mathematical correct way to write the range. The values of a and b determine whether the graph is increasing or decreasing. When a is positive, greater than 0, and b is greater than 1, this graph should increase from quadrant 2 to 1. When a is positive, greater than 0, and b is between 0 and 1, the graph will decrease from quadrant 2 to quadrant 1. When a is negative, less than 0, and b is greater than 1, the graph decreases from quadrant 3 to quadrant 4. And when a is negative and b is between 0 and 1, the graph will increase from quadrant 3 to quadrant 4. Also, the value of b affects the steepness of the graph as x increases. So when b is greater than 1, as x increases, the curve gets steeper as b increases. And when b is between 0 and 1, as x increases, the curve gets steeper as b decreases. Excellent. All right. So you guys know which questions you should do from 1 through 15. That's it. We're done.